Welcome to the lecture on the reflection on risk analysis. My name is Behnam Taebi, and I'm with the group of philosophy at TU Delft. Today's lecture is about two topics. In part one, I'll discuss the evolution of safety in reactor design and discuss various methods for guaranteeing safety in nuclear reactors. In part two, I will elaborate on the notion of acceptable risk and discuss the ethical issues of acceptability when it comes to risk acceptance. Let me start with the first section on the evolution of safety in nuclear reactor design. Evolution of safety in the reactor design is an important development. From the very beginning of the first reactor in 1942, where Enrico Fermi was building the world's first nuclear reactor, safety was an important issue. Safety was particularly important after nuclear accidents. In 1979, after the 3 Mile accident, a discussion started in the United States on how to make nuclear reactors safer. I'll come back to this discussion in a few minutes. When Chernobyl happened in 1986, the discussion on making reactors safer also reached Europe. It is still unclear to say how Fukushima has affected the design of reactors and the philosophy of that design. When we talk about reactor safety, there are 3 modes that we refer to. The first reactors were mainly actively safe, which means that they relied on external mechanisms, such as power or an operator. The more developed reactors were passively safe reactors. Passive reactors or passive safe reactors are those reactors that do not require human intervention. So they work based on natural laws, for instance, gravity. You do not need external power to be able to cool down the reactor. The most advanced type of safety would be inherent safety, which tries to eliminate or exclude inherent hazards through design. Let me talk about the probabilistic risk assessment and how that affected the development of safety in nuclear reactor design. Probabilistic risk assessment was first proposed by Rasmussen in 1975. It's a method with which we map all the events that could go wrong and we assign probabilities to each of those events, with which we try to conclude what is the probability of an accident, for instance, a core meltdown accident in a nuclear reactor. Rasmussen calculated that the meltdown risk of a reactor in that time, 1979, is 5 times 10 to the minus 5. That would be 5 times in 10,000 years, or once in every 20,000 years. Note, this is not regular years. We are talking about years of reactor operation, also referred to as reactor years. So based on 500 reactors, 1 accident would occur every 40 years. That was still within the acceptable margins. So the 3 Mile Island accident was roughly in line with what Rasmussen estimated to be the risk of a core meltdown. What was decisive for making reactors more safe was actually the anticipated growth in making more nuclear reactors. Right now we have about 435 nuclear reactors operable in the world. But in the 70s and 80s, it was anticipated that that number will grow to 5,000. So that would be 10 times more the number of reactors back then and right now. So we would go from an accident in every 40 years to an accident every 4 years because we would have 10 times more reactor operation years. An accident every 4 years was absolutely unacceptable. Therefore, reactors needed to be made safer. For making nuclear reactors safer, there were 2 methods proposed: incremental improvements and radical improvements. An incremental change in design is taking the current design as a departing point and trying to add safety features or removing unsafety features. There is another approach that would be the radical design, which starts from scratch and takes safety as a leading criterion when designing nuclear reactors. I am not going to go through this graph, but this is something that comes back in one of your reading material. What you see here is that there are different types of improvements, which are incremental improvements and radical improvement in designing new reactors. The probabilistic risk assessment as proposed by Rasmussen was mainly meant to identify and eliminate weaknesses in reactor design, by which we were hoping to make reactors safer. But nowadays, such probabilities are used in policymaking. For instance, the International Atomic Energy Agency argues that new reactors must have a core meltdown frequency, or a core damage frequency, the CDF, lower than 1 in 100,000 reactor years. So national legislators also use different varieties of such frequencies. What is equally important is that nowadays we are not only designing for safety, we also design for security, intentional harm, or avoiding intentional harm. We also design for sustainability, resource durability. All of these design criteria will be important, and in designing nuclear reactors, we come across different conflicts between these design criteria. Choices need to be made when we design nuclear reactors. Let me move to the second part of today's lecture on assessing the acceptability of risk. There is a gap in the literature between acceptance and acceptability. When we talk about acceptance, we talk about how the public will assess a new technology. Would the public accept the technology or not? The way I discuss acceptability today would refer to the broader societal and ethical issues. It will discuss the voluntariness of risk, the risk-benefit distribution, the multidimensionality of risk. So today's talk is not about the public acceptance. It is about the broader societal issues of ethical acceptability. First of all, there is the question of reliability of estimated risk. Both car accident and nuclear power meltdown risk would have more or less the same probability, timed impacts. So does that mean that we could talk about comparable risk or the same risk? The former, the car accident risk, would use statistical data, while the latter would use many assumptions, models, stimulations, and expert opinions in order to be able to assess the probability. There is also the Bayesian belief in risk estimations. Whenever we do not have enough information regarding a probability, what we do is actually consulting experts with authoritative opinions. Those experts are being asked to assess the risk and assign probabilities. This is needed in order to be able to quantify risk, but it will add a subjective element to risk assessments. The subjective element being the expert whose opinion is included in risk assessment. Next issue would be the multidimensionality of risk. We could assess risk in various dimensions, being fatalities, deaths, injuries, severe injuries, and many other units. Current risk assessments often take fatality as a criterion. This is in order to avoid any kind of discussion on what, for instance, constitute an injury and what would be a severe injury. Because about what constitute fatality, there could be no discussion. However, if we only focus on fatalities, we would reduce the multidimensionality of risk, because a measure could reduce fatalities but could bring many injuries. And the question would be, how could we take into account different dimensions of risk when we assess its acceptability? To put it bluntly, how to weight severe injuries and fatalities, or how many severe injuries would equal one death? The next issue when assessing ethical acceptability of risk would be informed consent. Many believe that consent or agreeing to risk is a primary ethical criterion. Informed consent argues that the party who is affected by new technology or by the new development should be fully informed about the consequences and consent to that risk. Only then we could talk about ethically acceptable risk. Informed consent is rooted in the moral principle of autonomy, arguing that an autonomous human being should be aware of the risk to which he or she is exposed, and that autonomous human being should also consent to the risk. Informed consent is very common in medical ethics. You might remember that your physician has asked you to sign a piece of paper in which he or she has discussed the risks of a new treatment with you. But it becomes very difficult when we talk about collective risk, because we could not give any veto rights as we do in the medical ethics. We could not give any veto right to every individual that is exposed to a collective technological risk. The next issue would be the distribution of risks and benefits. The distribution issue will come back in the lecture on a reflection on cost-benefit analysis, but it also determines the acceptability of risk, because aggregative methods, and those are the methods that add up different things, like the cost-benefit analysis, do not automatically deal with this issue. Also, risk assessment do not necessarily talk about the distributional issues. The question would be, to what extent could we impose risk on an individual or a group of individuals if the benefits of those risks are unevenly distributed? To put it differently, if we introduce new technology that brings risk to a local community but benefits to a country, to what extent is the imposition of risk on the local community ethically acceptable? Again, when it comes to medical ethics, the principle is rather straightforward. The patient should benefit from the risk to which he is imposed. But it would be much less straightforward for technological developments when it comes to the question of collective risk. Next issue would be the issue of uncertainty and how to deal with those uncertainties. Both uncertainty and ignorance are very important in technological developments. A notion that's been presented in the literature is the precautionary principle, which means that when there is no scientific evidence that there are no risks involved, that does not necessarily mean that you could go ahead and develop, because you as a developer have the burden of proof to show that there are no risks involved. There are also new approaches to technology, for instance, the approach that argues that new technology should be seen as a social experiment, which means that the ethical acceptability of new technology should be continuously assessed. In conclusion, in today's lecture, I presented first the safety of nuclear reactors and the improvement of that safety through different reactor design changes. I've also argued that we design nuclear reactors for other criteria than safety. In the second part of the lecture, I have discussed the social and ethical issues of risk acceptability. More specifically, I've discussed risk distribution, informed consent, and the precautionary principle. Thank you for your attention.